Alright, today we're going to be doing the Centripetal Force Lab. So remember, once you set an object in motion, it wants to continue to move in a straight line. Thus, if it moves on a curved path, there must be a force to keep it moving into the curved path. So there must be a force towards the center of the curve, and that is called the centripetal force. So that component of the force that keeps it in the circle is called the centripetal force. And so the apparatus we're going to use is here. I have this shaft that we can rotate, and the object we're going to be concerned with is this black weight called the bob. And to keep it moving in the circle, notice there is a spring here. So it's the spring force that supplies the centripetal force that holds it into the circle. So the spring is pulling it into the circle. Once I set the bob in motion, it wants to go in a straight line, but the string is holding it into the circle. Okay. Now we can easily measure the radius of the circle. There's a pointer here, and at the bottom of the bob it comes to a point, and so as I rotate this, I keep the bob lined up with the pointer, and that way I can measure the radius of the circle. So with a little bit of practice, you can rotate it so that it stays lined up with the pointer. So the bob stays lined up with the pointer. Okay? So that's what we're going to do. Now, what we need to do is measure the speed. And to measure the speed, I know the distance around a circle, of course, is 2 pi r, and noticing the radius, we know the distance it takes to go around one circle, and then using a stopwatch we can measure the time. But notice it goes pretty fast, so rather than trying to measure the time for one circle, we're going to measure 25 revolutions, and then knowing the radius we can get the total distance it travels, and knowing the time we can get the speed. And then from the speed we can use the centripetal force as v squared over r is the acceleration, and then times the mass of the bob. So first of all I need to find the mass of the bob, so we can disconnect the spring, and disconnect from here, and I can put it on the scale. Okay, so the mass of the bob is, there's 300 and 150, that's 450, 452.20. So 452.20 grams is the mass of the bob. Okay, now I'll reconnect it to my apparatus. Alright, so before I start measuring that data, I need to measure the radius. So I just measure from the center of this pointer to the center of the rotating shaft. I've already done that, but I'll do it again just to show you. And I have it set up so it's 16.0 centimeters. So the radius is 16.0 centimeters. And I can put the cm in parentheses in the column header. So all 3 trials, we're going to keep that radius. 16.0, we'll just write down the column for the radius. Okay. Then I'm going to use 25 revolutions, so the little n is 25 for all 3 trials. And that's revolutions. The time is in seconds. So don't forget to put the units. So we can put units in the column headers, so that way everything in that column is that unit. The velocity, of course, is going to be in centimeters per second. And the centripetal force, we're going to use CGS units, so this will be in dynes, so the dy. Okay, the hanging mass we'll measure later, and I'll show you what that is. Okay. So again, it's the spring that keeps the bob moving in the circle. So the spring force, if you recall from other labs, is proportional to the distance the spring is stretched. So F equals Kx, where K is the spring constant. So the spring force only depends on how far it is stretched. It does not depend on how much mass is on the bob, right? Only how far the spring is stretched. So as long as we keep the spring stretched the same distance, that spring force is constant. Now we're going to measure the centripetal force by measuring the time and so forth. And then after we're done with that, we're going to attach a string to the bob and then hang the string over here and attach a weight hanger and stretch this out until it lines up with a pointer again with hanging weights. And then that's a way we can measure the spring force directly by hanging weights until we get enough pulling force on the spring so that we can measure the spring force directly. And then we'll compare those two and find the percent difference. Okay? And they should be close to the same. Now I have to warn you, there is quite a bit of uncertainty or experimental error in this lab because it's very difficult to keep it exactly lined up with the pointer as you rotate it. And then plus, we also have some uncertainty with using a stopwatch. Right? But by using 25 revolutions, we can greatly reduce that uncertainty with the stopwatch for the random error from the stopwatch. Okay, so I'm going to practice a little bit until I can keep this lined up. Now once you get it going, it doesn't take very much effort to keep it going. Just have to give it a little bit of push. If I get it going too fast, it goes too far. If not fast enough, it doesn't go far enough. So the trick is to keep it lined up for 25 revolutions. Okay. Okay, I think I got the hang of it, so I'm going to get my stopwatch ready, and then I want to time 25 revolutions. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5. So I got 16.20 seconds. Okay, now we're going to do it again. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 1, 2, 3, 4, 5. 16.26 seconds. So the second round was 16.2 seconds, or 16.26 seconds. Okay, one more run. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 20, 21, 22, 23, 24, 25, 26. Oops, I went too far, didn't I? Start again. start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 21, 22, 23, 24, 25, 16.33. So the first run was 16.20 seconds, the second run was 16.26 seconds, and then the third run was 16.33 seconds. The radius, 16.0 centimeters for all three runs, and each run had 25 revolutions. So the rest of it's doing calculations. Okay, so next we're going to tie a string onto the bob and then hang some weights. So before I do that, I'm going to go ahead and pause the camera and get that part set up. Alright, now I've attached a string onto the bob, and I have a weight hanger. And I hang this over the pulley. And I'm going to put enough weights until I get the pointer on the bob lined up with the pointer of the circle. That looks about it right there. Okay, so now I need to count how much I have here. So I've got a hanger is 50, I have another 50, there's 100, another 500, there's 600, 700, and 20. 720 grams is the hanging mass. Okay, so then next I'm going to take the string off. I have it just looped on here, it should come right off. There we go. And this time I'm going to add an additional 100 grams to the mass of the bob. So I can loosen this nut here, put another 100 gram weight on here, tighten it down good so it doesn't come flying off in my face. So now the hanging mass, or not the hanging mass, excuse me, the mass of the bob now is increased by 100 grams. So that's going to be 552.20 grams. So the mass of the bob now is 552.20 grams. Now I'm not changing the radius, so I'm not changing the stretch of the spring. And remember, it's the spring force that supplies the centripetal force. But since I have more mass on my bob, then it should probably swing slower. So let's see if that turns out to be the case. You practice a little bit. Okay, I think I got it. You ready? Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5. 17.77. So 17.77 seconds for the first run. Again, 25 revolutions for the small n, and the radius is still 16.0 centimeters. Okay, put a stopwatch and then do it again. Get another run. It's a little bit harder to keep this one lined up, so there might be a little bit more experimental error with this. Okay, I think I got it. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5. 17.77 again. Oh, amazing. Okay. Third run. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5. 17.85. So the first run was 17.77 seconds. The second run was 17.77 seconds again. And then the third run was 17.85 seconds. Okay, now we added more weight on here, so again we're going to measure the stretch of the spring again. So again, we'll pause and set that up. All right, now I've got my string attached. I can put my weight hanger. Okay, it looks like it's lined up. And how much do I have? I have 100 plus another 600, 710. 710 grams. And 710 grams. All right, one other thing I need to point out is I made a mistake on the first run. I said it was 720 grams. I counted my little weight as 20 grams. It's really a 10. I had it upside down before. I thought it was a 20, but it really was a 10. So number one was also 710 grams from the hanging mass. So in table 1, it should have been 710 grams. So the same thing for data table 2. The hanging mass is exactly the same, 710 grams. Okay? All right, so the next thing we're going to do is we're going to remove this extra 100 grams, go back to the original mass for the bob of 452.20 grams. So in data table 3, the mass of the bob is again 452.20 grams. We're going to take this string off. And then I'm going to increase the radius. And so we'll increase the radius and see how that affects the centripetal force. And so I'm going to pause the camera while I set that up. All right, so I've moved the pointer out. And I think I've got it right at 20.5. Yes, indeed. 20.5 centimeters is the new radius. 20.5 for all 3 runs in table 3. Centimeters in parentheses in the column header for the units. All right, so this time we're going to have to travel faster, So instead of 25, we're going to do 30 revolutions. So the little end will be 30. For data table 3, the little end will be 30 revolutions for all 3 trials. And again, the time is in seconds. The velocity will be centimeters per second. And again, the force in dynes. Okay, so I'll get my stopwatch. Yeah, I have to spin it quite a bit faster to get it out there. Okay, I think I got it now. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 19, 20, 21, 22, 3, 4, 5, 6, 7, 8, 9, 30. 17.58. So the first run is 17.58 seconds. Reset again. It's a little hard to keep this one right on it. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17.62. So the second round was 17.62 seconds. Start. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 17.60 seconds. All right, so the first run in table 3 was 17.58 seconds. The second run was 17.62 seconds. And the third run was 17.60 seconds. Okay, so now we're done collecting the data for that. One more thing to do is now, since we've increased the radius, the spring is stretched farther. So we're going to have to measure the spring force again. So I've got 600 on my hanger right now. And of course that's not enough. So here's a 200, that's still not enough. Here's another 200, still not enough. Much. Almost. Too much. About right, maybe too much. Like that. Okay, that looks like it's right there. Now, it's not very precise, right? This 5 gram difference barely moves it. So So get the total. I got 100, another 5, 600, 7, 8, 9, 10. There's 1,000. 1,155. 1,155. 1,155 grams. So the hanging mass in table 3 is 1,155 grams. All right, so the remaining parts are just doing the calculations and answering the questions. And so that's it for the Centripetal Force Lab. All right, you guys can complete the rest.